Hello, everyone. Welcome to the 2021 ACOM seminar series. I hope you made it today. It's an unusual time. It's 11 o'clock here in Colorado because our guest today is joining from really far away, Doha, Qatar. Isn't technology beautiful? It's an honor and a pleasure for me to introduce Dr. R. Subramanian. Dr. Subramanian also goes by Subu, is a senior scientist at the Environment and Sustainability Center, ESC, of the Qatar Environment and Energy Research Institute, or KIRI. And at KIRI, he leads research on sensors for air quality and climate. He's also a research fellow at the Kigali Collaborative Research Center in Rwanda, a visitor researcher at Uzu CNRS in France, and an adjunct faculty member in the Department of Mechanical Engineering at Carnegie Mellon University in Pittsburgh, Pennsylvania. Over the past 2 decades, he has worked on chemical characterization and source apportionment of ambient organic aerosol, single particle measurements of black carbon and black carbon mixing state, cook stove and vehicle emission, and methane emission from natural gas facility. His recent accomplishments include leading the development of the real-time affordable multi-pollutant or RAMP monitor, co-leading the deployment of a 50 RAMP network in and around Pittsburgh in Pennsylvania, US. He also established the Africa Qualité de l'air or AfriqAir monitoring network, a collaborative international effort using a reference grade and lower cost monitors in many cities across sub-Saharan Africa, which is also the topic of his talk today. Before starting, I want to remind you that you can enter your questions down below and at any time in the talk, and I will read them out loud at the end. And with that, I introduce you to Subu. Subu, take it away.
Great. Thank you so much, Alessandro, for this introduction. And thank you again for the invitation to give this seminar at NCAR. I don't know if anybody still is around. When I was at NCAR, I mean, I used to work in Boulder at Droplet Measurement Technologies and participated in ICE-T and ISIL, those field campaigns. So, you know, maybe I ran into some of you at that time. Yeah, it's been a while, and good to be back at giving a seminar at NCAR. I'm really honored by this. And so today I'll be talking about our work that I've been doing over the last several years in measuring air pollution across many cities in sub-Saharan Africa. A lot of this work has been funded by the Make Our Planet Great Again a program established by President Emmanuel Macron in response to the United States pulling out of the Paris Climate Agreement. And I think we are all, you know, probably can feel reassured that the US is back in the agreement, and hopefully Glasgow will lead to, you know, better futures ahead. But, you know, out of that withdrawal came this project. So for personally, I mean, we've done hopefully a lot of good work in Africa, and we'll be sharing some of those results here today. My core team includes Michael Giordano, Julian Bahino, Carl Mehlings, who is now at NASA, Matthias Beekman, who is the Director of Research and Director of OSUFLU, as well as a huge host of collaborators in the AfriqAir and MOPGA team. Obviously, this is just a sub-selection of the names. AfriqAir initially came about through contacts, actually a lot of them on Twitter. So it's a great way to connect with people, and we have a lot more partners, but I'm probably missing a lot of names on this. And the funding is from the Make Our Planet Great Again program. The US EPA funded some of our work in Pittsburgh to develop the RAMP, and now we have we have funding from NSF AxelNet, at least for Carnegie Mellon, Columbia University, and Washington University St. Louis to develop a network of networks. So what I'm going to talk about today is briefly, I'm going to talk about air pollution, air quality monitoring, which of course none of you need an introduction to, but also about low-cost sensors, present some of the AfriqAir results from different parts of Africa, talk about spatio-temporal variability in urban areas, source apportionment that we can do with some LCS monitoring, how can we use that to complement satellite retrievals of surface air pollution, as well as talk a little bit about rural air quality, which is not the focus of this talk, but something that to keep in mind. And I just want to start off with the last slide first, which is, I'm sure, unusual, but I'll, you can refer to these points as we go. This is, part of the tell them what you're going to tell them, and then tell them what you told them approach, I guess. So we're using hybrid air quality networks to look at spatio-temporal variability in air pollution in cities across Africa. What we know and through experience is that the LCS data need to be corrected by collocation with reference monitors. But once corrected, they can qualitatively identify local and regional sources, track trends, plus also identify the extent of an air pollution problem, as well as the effectiveness of various air quality mitigation policies and lots of other things that I'll talk about today. Of course, traditional approaches that we as atmospheric scientists and atmospheric chemists are used to are still absolutely necessary. I'll talk about some of the things where low-cost sensors actually fall short and how traditional methods can take that science further along. And finally, we obviously need to invest in key infrastructure. Low-cost sensors are great, but oftentimes, especially in many cities in Africa, we use them because there is no basic infrastructure. And so we need this basic infrastructure in place. We also need to support local scientists, because without them, none of this work would be possible. We need to train the next generation of scientists and air quality practitioners, because helicoptering global north scientists like myself will probably come in and leave when funding runs out, or do one-time studies. But what happens on a long-term basis, that is not sustainable. And so we actually need to fund research by local scientists. We need to build infrastructure that is long-lasting, and essentially that is a way to leave a long-lasting, sustainable legacy. Of course, this is a famous slide. I'm sure you've seen a lot of this over the years. But essentially, air pollution is responsible, in case anyone didn't know, the estimates are about 7 million deaths a year from air pollution in 2019, according to the Health Effects Institute and the Global Burden of Disease. Particulate matter is a key pollutant. PM2.5 mass is what I'll largely focus on today. Of course, there are also gaseous criteria pollutants, ozone and nitrogen dioxide being key as well. And you might have followed the recent furor over the update after 15 years of the WHO guidelines as well. And when we talk about traditional approaches, what are we talking about here? Traditional monitors that typically cost $10,000 to $30,000 for each of those instruments. They require air-conditioned shelters. They are highly accurate, but they also require frequent maintenance. They are sparsely distributed even in urban areas. So for example, this is a Paris map of nitrogen dioxide that I obtained from OpenAQ, a city of about 12 or 13 million people. That's about 12 or 13 monitors, so maybe one per million people. Still, there can be hotspots that are not monitored because there are a lot of high traffic roads in the middle, which are not close to a monitor. So, they are still relatively sparsely distributed. And of course, they're missing in many African countries. So, this is a photograph from Rwanda, of course. My friend Jimmy Gasore, Theo Habineza, and Professor Michael Guattari at the University of Nairobi. Jimmy is a professor at the University of Rwanda, and they established this air quality monitoring station at Meteor Rwanda in Kigali. And this is Theo showing off the instruments in there. You might be very familiar with the Teledyne instruments over there, the Teledyne Blue. But there's very few of these monitors in many of these cities, especially comprehensive air quality monitors that measure PM2.5 as well as gaseous pollutants. So we try to complement that, or at least get a start on estimating what is the level of pollution in these cities, and many of these cities using low-cost sensors. And so this is the background here. This is the ramp that I've deployed at the University of Rwanda. They typically cost anywhere from $250 for a purple air monitor that many of you, I'm sure, have, to $10,000 for a box. The ramp is somewhere in the middle of that. Relatively small footprint, low-cost sensors, low-power sensors. They can be solar-powered. But they're also affected by temperature and relative humidity, because to keep the cost down, we don't actually employ any sort of air conditioning. And they might also be cross-sensitive to non-target species. So we need to actually carefully characterize them before using that data. And this is a picture of me with the 4 students at the University of Rwanda. This is Clavers in the Iaga. This is Sandrine Guhirwa, Valerian Bharane, and Safari Kagabo, who Valerian and Safari are now lecturers at the University of Rwanda. Sandrine works at Media Rwanda. So a lot of the stock, some of the stock will talk about results using the RAMP monitor, which was developed by my group at Carnegie Mellon in collaboration with Sensevier, a small company in Pittsburgh, now owned by Senset Technologies, Senset LLC in Indiana. It uses, like a lot of other boxes around here, it uses electrochemical sensors for carbon monoxide, ozone, nitrogen dioxide, and sulfur dioxide. I don't think it's a secret that most of these boxes use alpha sense electrochemical sensors. We use optical nephelometers for PM2.5 in the picture here. We used MET1 neighborhood PM monitors. We have also used purple air monitors or plant tower sensors themselves. They transmit data using GSM, cell phone connection, have an onboard SD card. We have published several papers on calibration of these sensors. And the way that we calibrate these sensors is there's a couple different ways. Number one, the traditional way that you would calibrate a reference monitor is to have preset concentrations of gases or mixing ratios of gases being fed to the reference monitor. That is one possibility. The other possibility is to collocate the sensors. And so you can see the banks of these ramps next to the Carnegie Mellon Mobile Air Quality Lab, which has a reference monitoring station inside an air-conditioned chamber. And we're running the sensors as we would in the wild, as you were, and we map the sensor response as a function of temperature, humidity, and other pollutants that we can measure to the reference monitoring concentration of the target analyte. And this work was led by Naomi Zimmerman, who was a postdoc at Carnegie Mellon and is now a faculty member at the University of British Columbia in Pittsburgh. And we found that the field approach using coupled with machine learning techniques like random forest actually works really well for getting good data quality out of these electrochemical sensors. So the green boxes are the performance of the monitors using the lab-based calibration approach. The blue boxes are the simple multilinear regression, which still works pretty well for carbon monoxide. The magenta box is the random forest model, which works really well for carbon monoxide and ozone. NO2 is still a challenge, but that's partly because the NO2 concentrations in Pittsburgh are pretty low, usually about annual average of what 11 ppb. But essentially, all of these values with low-cost sensors and carefully calibrated low-cost sensors and these machine learning approaches are either better than what the EPA guidelines are for hotspot monitoring. So the hotspot monitoring is tier 2, supplemental monitoring is tier 3, and basically tier 2 and tier 4 are at 30%, tier 3 is about 20% precision and bias. So we can do better than supplemental monitoring for carbon monoxide and ozone, and we can do better than hotspot monitoring for nitrogen dioxide. So that is in Pittsburgh. And of course, with PM sensors are more of a challenge, and part of the reason that I don't normally share uncorrected low-cost sensor data with anyone, and probably a lot of people hate me for not doing that, but it's because of this graph here. Basically, the purple air monitor, as reported, shows a significant bias in concentrations, particularly tied to relative humidity compared to the reference monitoring station. And this is for all sorts of reasons that we can go into if you want. But we can develop some corrections that bring it closer to reality. And so this is a lot of what our work is currently focused on, building these calibration models all over Africa. Talking about Africa, so what do we know about air pollution worldwide? And these are maps from OpenAQ, which is a fantastic resource. Krista Heisenkopf has done a great job with OpenAQ, and the team is carrying it on pretty well now. So looking at low-cost reference and low-cost sensor data all over the world, you can see there's a few PM2.5 monitors across Africa. The square boxes are low-cost sensor data. Again, there's a lot of low-cost sensor data in Africa, but not a lot of reference monitoring outside of South Africa. Of course, this is publicly available data. And so there may be cities and countries where there are reference monitors, they just don't make it available openly. And for NO2, there is very little data at all. And so if you look at, so we looked at the, so you get satellite estimates of pollution worldwide, and we compare it to what we think are the PM2.5 monitors of reference monitors per million people. The cleanest cities and cleanest country regions in the world, this is, Western Europe and North America, are typically the most well monitored. And I mean, I'm sure many of you are very familiar with this concept, but a lot of the places where pollution is pretty high, there is almost 2 orders of magnitude fewer monitors, maybe 0 monitors in a lot of these places. And this comes back to the title of my talk. You can't really manage what you don't measure. And a lot of our work is really trying to measure air quality in many of these fast growing cities so that we can look at air pollution, quantify the extent of the problem, and try to find solutions to reduce air pollution. And a lot of this work has been funded for me by the Make Our Planet Great Again program, which for me started about 3 years ago this month. Actually, this week, it'll be 3 years exactly. So through that, we've deployed a lot of monitors in Kenya, Ghana, Cote d'Ivoire, South Africa, plenty of other places, and working with local collaborators. So our website here, afriqair.org, which some of you are familiar with, and AfriqAir Quality, we're on Twitter. We're pretty active on Twitter, and a lot of our network actually comes on Twitter, so please connect with us there. Our email works too, of course. Going on to the results a little bit here. And this is the first project that we started. This was the, I guess, the prequel to AfriqAir, where I was at Carnegie Mellon, and we bootstrapped some few $1,000s together from my friends Paulina Jaramillo and Alan Robinson. And we deployed monitors at the University of Rwanda, which is shown here, as well as Gachuriro, which is the residential area. This is essentially Paulina's house when she was living in Rwanda, in Kigali. And so they're about 5 kilometers apart. We conducted the study in collaboration with Jimmy Gasore, Langley Dewitt, and others, and of course these the students here. And we carried the study for about 16 months. And so this was sort of the first long-term air quality data set for Kigali. And over these 16 months, the average PM2.5 was about 52 microgram per meter cube. In 2018, some of the concentrations appear to be lower than 2017, but all throughout, the concentrations are much higher than the WHO guideline, which is currently at 5 microgram per meter cube, even exceeding the WHO interim target 1 of 35 microgram per meter cube. Actually, the 35 is, I think it's still the interim target in a while, but the concentrations are exceeding that. So we did observe a bit of seasonality with this monitoring. So we started in March of 2017. So March, April, May is the wet season in Kigali. June, July, August, September is the long dry season. October, November is a short wet season. December, Jan, Feb is a dry season, and another March, April, May is a wet season. And you can clearly see that dry seasons experiences more PM2.5 pollution than the wet season. And possibly due to washout of transported regional background emissions. But this is something that we still need to investigate further. Expanding beyond Kigali with the help of the MOPGA grant, we were able to deploy many more monitors in many cities. So Abidjan, Cote d'Ivoire, Accra, Ghana. This Wellhorn, South Africa was a collaboration with Becky Garland. In Accra, in Ghana, we were working with Kofi Omega. Seen here also are Mr. Emmanuel Apu of the Ghana EPA and Alison Hughes at the University of Ghana. This young man here is Julian Bahina, who's a postdoc working with me on the MOPGA project. He got a MOPGA fellowship as well. This is Veronique Boye at the University of Felix Houphouët-Boigny in Abidjan, and her team here. The Samdala, we deployed a monitor here along working with Stuart Pickett. So he has a reference monitoring station in this semi-urban area, which is a lot of low-income communities. And so we were able to deploy a couple of monitors there. This is Dan Westervelt from Columbia University deploying a monitor at this mast that was set up by Sean Khan at UNEP outside the Kampala US Embassy. So basically, proximity to the US Embassy BAM to develop a calibration for all of these low-cost sensors over here. We were able to deploy some monitors. So Professor Michael Guattari at the University of Nairobi finally deployed a BAM 1020 at the University of Nairobi. This is Ezekiel Waiguru, who was working on his master's program at the University of Nairobi with Michael, and is now doing a PhD with my group in France. And so we were able to deploy a bunch of clarity nodes to collocate to the BAM there. Of course, like I said, data quality is we need collocations to establish data quality and correction factors for these low-cost sensors for a variety of reasons, including aerosol composition and size distribution and hygroscopic growth, obviously, as a result of that. And so we need to establish these collocations first before we can actually be assured of the data that comes out of these low-cost sensor networks. And so we have some results from all of these networks. This is the Wellhorn, which is a rural site. Obviously, these are not great, perfect correlations. So this is something that we need to look into further. Nairobi, a BAM compared to the purple arrow over here, or Accra, this is a quantQ modular PM 2.5 monitor compared to the US Embassy BAM, which actually works pretty well, at least at this location. And part of the reason is that Evan Cross and David Hagen at quantQ have incorporated some aerosol chemistry into their correction factors already. And so we get some pretty nice performance out of the modular PM, at least in Accra. And so I guess the one question is, well, why do we need all of these collocations? Why can't you just take a correction factor that's already available, developed somewhere, and why don't you just apply it everywhere else? We actually looked at that, and obviously this is painful to do it in every city. And so we looked at the Samdala South Africa data set, and this is work led by Michael Giordano, who is the executive director of AfriqAir. I should have put Mike's photograph on here, but sorry for that, Mike. But the gray bar here is the purple air data that's raw without any correction as reported data compared. And so this is the three metrics that we normally use: mean normalized bias, the bias corrected CBMAE, and the correlation using a Pearson R. Of course, correlation is pretty unchanged with with any model that we use or with the raw data. But the mean normalized bias, so any correction actually, because we apply any correction, whether it's a general, this is a US EPA model that was published by Caroline Bark-Johnson, whether we use the rural Wellhorn model or a semi-urban localized Samdala model, it produces lower bias than the as reported data. So any correction is better than as reported data, but some corrections are better than others. Now, if you look at the bias corrected CBMAE, the Wellhorn model performs worse than the urban US EPA model or the Samdala model, for example. But obviously, the Samdala South Africa specific model eliminates measurement bias. So it's for almost zero here in the salmon color, and has the lowest CBMAE, also the highest Pearson R. And so that's why we require localized calibrations, and that's why we're doing all of this work across the continent. And so our work in Nairobi, we started in about, I think, late 2019. And I think this came out of a conversation that I had with Emilia Turnstom, who was then at the University of Wisconsin. And we were having dinner at Big Mama's Fish Place, I think. And we just talked about air quality, and she's an economist, and she's trying to understand why. And so her plan was to deploy 20 plus clarity nodes at schools across Nairobi to look at the effect of air pollution on student performance. For all sorts of reasons, that project sort of fell through. And We ended up collaborating along with Dan Westerveld, Faye McNeil, Albert Presto, Paulina Jaramillo, and myself, and Emilia to deploy 20 plus Clarity nodes across Nairobi. And the Clarity nodes landed in Nairobi in January, and we were trying to get permissions with the schools. And then March 2020 happened, and yeah, basically we lost all access to the schools at that point of time, and that has continued for about a year. Yeah, we had several sensor nodes collocated at the IPA office for a year, so there are some interesting results as well. Now several sensor nodes are collocated with Michael Guattari's BAM 1020 at the University of Nairobi, and with the NOx analyzer that Dan Westerveld installed along with Gordon Opinde at the Kenyatta University City Center campus. So we're getting some localized calibrations for the PM2.5 and the NO2 out of the Clarity nodes. And for PM2.5, again, this is going back to the necessity for localized calibration. We applied various other in Accra, Wellhund, US EPA, Zamdala, Kampala models to the Nairobi dataset. But the localized Nairobi calibration performs best of all. So there's the dark gray bar, lowest bias corrected CBMA, almost zero bias. Pearson correlation is also higher. So again, what we see in Zamdala, we also see in Nairobi, in that a localized calibration works best of all. And now we have a few sensors actually deployed around Nairobi, not just at the IPA office or at the University of Nairobi. And this was some work for, on the ground work done by Ezekiel Waiguru while he's waiting to come to France to start his PhD. And so now Waiguru is now looking at the NO2 data, and these are not yet corrected. We started doing some collocations with Dan's reference NOx monitor, but this is data from 2020, and this is actually, he showed me last week, which is really interesting. But just taking the raw data from the Clarity nodes, and this is the first quarter of 2020, this is the second quarter of 2020, third quarter of 2020, and fourth quarter of 2020. And the same 7 nodes, and you can see that in the first 3 months, the performance is actually pretty consistent, at least reasonably consistent, except for the black line here. Even in the Q2, the performance is pretty consistent. Q3, not as good. Q4, things are definitely getting bad. And so we continue to have the monitors deployed all through 2021. And Waiguru will be sending me that data. I'm pretty sure it'll look a lot worse than this. And this is something that we actually saw in Pittsburgh as well. So this was a paper that we published recently in ACS Sensors, because the NO2 sensors are essentially just an ox sensor, an oxidant sensor that has an ozone scrubber. And so as long as the ozone scrubber is working, ozone is not coming through, only NO2 goes through, and that's what is detected as NO2. So you see in the first 3 months, R-square of 0.68, even with a raw sensor signal, so looking great. A machine learning model applied gives an R-square of 0.95, fantastic, worked great. After a few months, the ozone scrubber is getting depleted due to ambient ozone concentrations. And so now you see a little bit of ozone along with a little bit of NO2 coming in, R-square of 0.32 with the raw data, R-square of 0.5 with the machine learning model, still decent, not great, but okay. And then after about a year or so, 321 days after opening, so essentially you open the sensor and you put it outside exposed to ozone, it starts aging right away. And so R-square is basically 0 at that point of time with the raw data. So the sensor is not really responding to NO2, but if you apply a machine learning model and you put in other, covariants, for example, you might actually get some decent performance. So your machine learning model, if you apply it to your sensor, it might mask the fact that your sensor is shit. Pardon my friends there. But essentially, we at this point say that these electrochemical sensors in areas where ozone concentrations are relatively high, like Pittsburgh, you might see 70, 80 ppb periodically. You should change the NO2 sensors every 6 months, at least every year in places like Kigali, where the NO2 concentrations are ozone concentrations are more moderate. So talking about actual results in terms of spatio-temporal variability of PM2.5. And so this is work led by Dr. Julian Bahino, along with his PhD advisor, Veronique Boye, Professor Kofi Omega at the University of Cape Coast, Professor Alison Hughes at the University of Ghana. Of course, Professor Veronique Boye is at the University of Felix Houphouët-Boigny, as well as their students. Into deployed monitors at the University of Felix Houphouët-Boigny. There is a US Embassy BAM that we use for this analysis. There is a ramp deployed at the Abidjan City Hall. And similarly, we have ramps at the atomic interchange in Accra, Kwashimian Trinity Church, as well as this is a purple air actually that Kofi had deployed a while back, and then the US Embassy BAM. And what do the results look like? I mean, these are still pretty relatively new results. We're working on calibrations for these sensors till this summer. And so we're now finally starting to see some of the corrected data. And so this is the Abidjan Embassy. This is a BAM. So about 25 microgram per meter cube median. Abidjan City Hall is about the same, but the university is much less in PM2.5 concentration. This is Accra. Again, Accra US Embassy, median about 20 microgram per meter cube. Atomic interchange is about the same. Kwashimian Trinity Church, a little bit less. The Zorwulu sensor reports much higher concentrations, but this is a purple air that we have not corrected for. And so that this difference could be, some of this could be explained by the fact that the purple air is positively biased at high RH, so we need to correct for that. But we see some, and even the shapes of these distributions are quite different from location to location, which suggests that even if the medians are about the same, they don't all experience the same pollution at the same time. And so there may be spatio-temporal heterogeneities in pollution that can be revealed using a low-cost sensor network. So, and so a little bit, and so some of the precursor to AfriqAir is the fact that the Purple Air company and Adrian Debward gave me 5 Purple Airs for free after I gave a talk at AQMD a few years ago. And we gave away a couple of monitors to Dan Westervelt, and he deployed it at Kinshasa, and 2 of those monitors went to Becky Garland at CSIR in Pretoria. And so she deployed a Purple Air at Belhaven, where we developed a collocation for that, collocation-based calibration for that. She deployed a Purple Air monitor at her house in Centurion, close to Pretoria. And so if you just compare the Purple Airs in Belhaven and Centurion, we take the Belhaven calibration, apply to Centurion, and we find that Centurion, Becky's house is much more polluted than the rural spot, which may not be a surprise. But this was a surprise to Becky because the SACIS reference monitoring station, which is the South Africa reference network, the impression is that it is deployed at areas of high pollution, and it's expected that suburban areas, residential areas like Centurion would be less polluted than the SACIS networks. But when we compare these data to the SACIS network, nearest SACIS station, the data are actually quite comparable. And so there is a potential for these low-cost sensors to reveal these higher pollution areas where the reference monitoring station does not exist, even if like in South Africa, there is a good reference monitoring station in place. And this is a collaboration, obviously, with Becky Garland, Peter Van Zyl, Stuart Pickett, and Brigitte Language, and others at Northwest University. And of course, Becky is right now at CSIR, though she is soon moving to the University of Pretoria. So the 2 Purple Airs that Dan grabbed, they went to the US Embassy in Kinshasa, and he has been working with the State Department at the US Embassy there to deploy the monitors there. And he also deployed a lot more Purple Airs in Kinshasa and Brazzaville subsequent to that. And we published this paper. The first author is Celeste McFarlane, who is actually an undergraduate, and she just graduated from Columbia, a really smart young woman. And so she wrote this paper, and we got some really nice results looking at ambient PM2.5 concentrations. Now, there is no reference monitoring station in Kinshasa, so we took the Kampala collocation, which seemed like a reasonably reasonable proxy in terms of AOD and geographical characteristics. And we applied it to the data in Kinshasa. So the data may need to be fine-tuned using a local reference monitoring station, but we do see significant spatial and temporal variability, again, just like we did in Kigali. And so Dan's continuing to work establishing sensor networks in Kinshasa and Brazzaville, and hopefully we'll get a TEOM there as well. Speaking of which, so a lot of these places don't have reference monitoring stations. So where do we go from here? The low-cost sensors are useful to establish a baseline, get an estimate of the problem, but we do need reference monitors as well. And so we are lucky to get 25 TEOM PM2.5 monitors. These were being retired from the UK Urban and Rural Network. I think it's called the Automated Urban and Rural Network, AURN, and through Christine Brabant and with support from the Clean Air Fund and the UK NERC, we were able to test some of the TEOMs to make sure they're working and then ship them, 15 of them to Kigali at the Kigali Collaborative Research Center and 10 of them to the University of Cape Coast with Kofi Omega. And so this is Kofi's team. I believe that's Christian Sivar looking at the TEOM that's set up at the University of Cape Coast. And this is Mike Giordano here, as well as this is another technician who works with Jimmy Gasore. I forget his name, apologize for that. And these are the TEOMs at the KCRC. So Mike's just spent a few weeks in Rwanda and got these TEOMs working, and hopefully they will be deployed in Rwanda. So that's 25 TEOMs, which is a huge expansion in air quality reference grade air quality monitoring for many of these countries in this region generally. This is in addition to the 2 BAMs. We have deployed a BAM in Abidjan and a BAM in Nairobi, as well as a NOx analyzer in Abidjan, a NOx analyzer and an ozone monitor in Accra through the MOPGA project. Dan Westervelt has deployed a NOx analyzer in Nairobi. And so these will provide collocation-based calibration for a low-cost PM and with the NOx and ozone monitors for the gas sensors as well. We can also hopefully train the local STEM workforce, but if we do require additional funding for our in-country partners and to finance the installation and operation of all of these monitors. Because it's great that they're there, but they do require supplies. I mean, our colleagues and scientific partners and technicians, they do require support as well to continue this research. So I think still okay on time. So satellites do provide spatial coverage. I mean, so this is talking about low-cost sensors and satellites. And so satellites obviously provide spatial coverage, but we do need surface monitoring for ground truthing. Part of the reason is that satellite passes often occur in the middle of the day. For example, here in Kigali, when it's the cleanest. And so we require ground monitoring to capture the diurnal pattern of pollution. At the same time, with just 3 or 4 monitors in Kigali, we will not be able to have the spatial coverage that the satellite data provide. And so we need to combine the two to get the maximum benefit. And so we looked at that, working with Carl Mehlings, who was a postdoc at that time, working with me on the MOPGA project, and is now a postdoctoral fellow at NASA. And so what we looked at was, if we assume there is just 1 monitor in a city, so we had 2 monitors in Kigali for this graph. And so if we assume that 1 monitor is all we have in a city, how well is it representative of another site? And on the other hand, if we combine it with the satellite AOD and use satellite, that conversion factor and satellite AOD at the second location, how well does that perform? And we do find that the satellite LCS combination has much better correlation coefficient, narrower spread of R, narrower spread and lower CVMAE over here, as well as narrower spread of bias, especially the mean absolute error is reduced on median by about 40%. And so there is potential for low-cost sensors to be combined with satellite AOD, just a simple straight-up combination. Of course, there's some complicated math involved, and Carl is the expert on that. But but that's definitely good potential as well for combining low-cost sensor networks and satellites to get increased knowledge about air pollution in these cities. And so we published that paper in Atmospheric Measurement Techniques. And now we're at NO2, and I'm sure there are some tropomy experts in the room. I do not claim to be a tropomy expert, but we, by any means, but initially we deployed a reference NO2 NOx analyzer at the University of Ghana, and just looked at the first couple of weeks of data. And so looks great. An R of 0.71 will help a little bit with the high point here. Still looks promising after about 2 weeks. And then now we are a year later, doesn't look that great. And there are definitely some high values in the tropomy retrieval. So this is a 5 pixel by 5 pixel average. We were told don't pick 1 pixel, pick an average of surrounding pixels. Plus we are comparing it to a point measurement. So not exactly apples to apples, but still there is, short-term campaigns, I'm sure all of you are very familiar with this, but short-term campaigns may not necessarily give the full picture. We really need long-term campaigns. And so I just did a monthly box and whiskers plot. And again, there's some really interesting results, I think, here, even with a simple analysis. And that, number one, the University of Ghana seems to see only about 5 ppb of NO2 all year round. Maybe it's a bit of more of an urban background site that's possible away from roads. But we do see a sharp increase in the tropomy NO2 in December and January, which are the dry seasons, where there may be more forest fires a lot, and that may be leading to higher NO2 in the tropomy. Yeah, I mean, there may also be surface spatial variability, right? Because this is just 1 point measurement compared to a 5 pixel by 5 pixel retrieval. So there's a lot more work to be done. And so what do we do next? We definitely, talked a bit with Jim Crawford and his team about the Pandora instrument and whether we can actually get vertical profiles for NO2. Whether you want to look at aerosol's composition and size distribution, include as a function of time and space as less, including altitude. And I'm sure there are more ideas that you all can tell me about and we can discuss. But again, that's not my forte, and happy to have more discussions on this front. And so we do have low-cost sensors. We did not have actual chemistry or an ACSM or an AMS that we are used to in the US and EU. But can we still get some estimates of what are the sources contributing to PM2.5? And this was an idea suggested by Spiros Pandis, and his group has published a couple of papers on this method, so we decided to go along with that. And so initially we have this typical seasonal diurnal pattern for the wet season in the green and the blue season, and the dry season in the blue. And there are 5 seasons over here. Not super consistent, but still kind of instructive. We first of all see that the dry season, as we saw before in Kigali, seems significantly higher PM2.5 pollution, as much as 20 microgram per meter cube, more polluted than the wet season. Also, we see a pretty sharp diurnal, which could be transported for as fire emissions. And Langley Dewitt has written a nice paper out of the Mugogo Rwanda Climate Observatory talking about this. And so we definitely need to do more work on that front. There is a sharp diurnal profile in PM2.5. So this is at Kigali, is a typical city like any other. You see a morning rush hour peak and maybe an evening rush hour peak. We also had a black carbon monitor there, a typical Met1 black carbon monitor like an anethelometer. And we see a similar diurnal profile for black carbon. If you look at the wavelength dependence of particulate light absorption, the Angstrom absorption exponent, it appears that the AM morning peak is from vehicular traffic, but the overnight peak here is from vehicles and domestic cooking potentially. So going by Spiros's method for what should be the regional component, which basically assumes that if the minimum here in the seasonal diurnal profile is regional background, and anything above is a local contribution. Then during the wet season, about 50% of the PM2.5, so it's about 20 something on an average, like 40 something all day. So about 50% is from local source, is from regional sources, 50% is from local sources. In the dry season, the minima is much higher fraction of the average PM2.5. And so during the dry season, about 75% of the PM2.5 in Kigali may be from regional sources and only 25% from local sources. So this speaks to the importance of what mitigation plans do you put in place for local air pollution control versus regional air pollution control. But again, and this is and again, coming back to the point of aerosol chemical composition, I apologize for a little bit of the haphazard nature of the presentation, but we are now looking at the MERA2 estimates for urban PM2.5 composition. I'm not sure how much to trust this. We just put it together at the last minute. And basically, we're trying to see if we can use that to correct our low-cost sensor data, but also it's instructive to see what models think are the sources of pollution in these cities. Dust in Accra is 75%. I'm not sure about that. But again, this comes back to the need for ground measurements to verify global and regional models. They're required for source apportionment studies. For example, half my PhD was on chemical mass balance modeling of PM2.5 on organic aerosol using molecular markers. And that requires knowledge of chemistry, obviously, GC mass spec, things like that. But we are here, we just have low-cost sensors so far. And so we would need chemical composition size distribution to improve data quality, as well as source apportionment studies, and to verify global and regional models. I learned recently that there are studies being conducted in major cities by the World Bank, which is a great start. But the question is, what happens if we put policies in place? Vehicle fleets change, industry develops, because a lot of these cities are fast-growing, rapidly industrializing cities. You do a one-off study, what happens in the future? So in that front, we need more investments in infrastructure, like Jimmy Gasori has an ACSM. We are working with him on that, but we need to get that operational. But again, we need high time resolution for PM composition in each major city, which can be defined as cities with a population of greater than 250,000 people, for example. We do need this to invest in these measurements, which will enable long-term studies to capture seasonal changes, enable source apportionment, as well as train local students, hopefully masters and PhD students, who can then go on to be part of their regulatory agencies or scientific capacity, who can then generate their own source apportionment studies, their own air quality management plans, and implement their own policies, because local people know what's best for them. So another way, that just an example I threw in here, this is really interesting. Kigali has a car-free day, which is basically not entirely car-free. It's some of the major roads are closed for traffic on one Sunday or two Sundays a month. And we looked at our PM2.5 data here during our 16-month study. So the car-free Sunday average PM2.5 is on the y-axis, and the regular Sunday average PM2.5 is on the x-axis. And we see that during the periods typically when around 7 a.m., 8 a.m., the PM2.5 is much lower on the car-free days than on the regular Sundays. And so this suggests that the car-free days do have some effect, but we definitely need more studies, perhaps with roadside monitors. We also see this effect with black carbon. But again, this is one way that low-cost sensors can be used to track the effect of what might be mitigation strategies to reduce air pollution in these cities. Finally, I think I'm out of time, but I just wanted to mention some of this started with our measurements in rural Tanzania. This is Nathan Williams, who's a professor at NIT, and our colleagues at a local company over here, and installing solar microgrids. And we went to rural Tanzania over here. And I just carried an Aerosol battery operated portable low-cost sensor, measured concentrations around these very rural, non-electrified villages. One of them even had no running water. Of course, obviously, everybody knows indoor air pollution from cooking is probably the most polluted. So this is this part over here, which is about 450 microgram per meter cube of PM10 and about 200 microgram per meter cube of PM2.5. But even other locations at pretty high concentrations apparently, and these are the portable monitors, so data have not been corrected, so there may be some overestimates there. But even the smaller village of Bugarama had higher levels of PM than the higher towns, and some of these values are pretty comparable to urban cities in Rwanda apparently. So even if it's like a factor of 2 overestimated, you are still talking about 30 microgram per meter cube of PM2.5, which is still pretty polluted, honestly. And so this is something that, we focus a lot on urban air quality, but a lot of rural areas where people do live. And a lot of this pollution happens because of open cooking, for example, or dust. And a lot of children are playing around in the areas where a lot of the smoke is. So that can have serious health effects that we may not be looking at. To wrap up, where do we go from here? Again, what's the future here is essential infrastructure and capacity building that we need to work on. We need to have ground measurements to verify global and regional models, improve satellite retrievals, improve satellite data quality. Required for source apportionment studies, we need probably an ACSM in every major city, right? It sounds like FDR with chicken in every pot, but we need an ACSM in every major city along with a reference monitoring station and a network of low-cost sensors. Long-term studies are essential to capture seasonal changes, and build local capacity obviously is a big thing because you can do one-off studies, but what happens after that? That is useful, but it's not sustainable long-term. And so again, coming back to my title slide, and with that, I'll be happy to take any questions. A shout out to CAMSNet. This is part of the Network of Networks project that is funded by NSF. And so we are organizing a special symposium at ASIC, which I'm also an organizer of. While the ASIC's abstract, I think deadline is today or this week, CAMSNet session, we welcome not just CAMSNet partners, but also others to come visit us and be part of this parallel session at ASIC. And the abstracts will be, you can submit an abstract on November 29th. And this is focused on low-cost sensors. And with that, I'll be happy to take any questions. Thank you for your attention.
Awesome. Thanks, Subbu. That was super interesting on a topic that I certainly need to know more. Oh, we have already a few questions. That's great. Ben is asking, did you use a model to convert the tropomy column surface equivalent data for the comparison with the surface of observation?
Nope. We just, and we had a grad student go into the and look at the tropomy, again, volumetric column thing, VCD. So again, I'm a complete ignoramus when it comes to tropomy, and I'm happy to be educated on this. But we just took the molecules per centimeter square, I think, and then just used that. Yeah, we didn't actually apply any models. This is something that I think, yeah, and the long-term thing, yeah, I mean, we still are working on that, but these are really preliminary things, and we still need a lot more work on that front.
Anonymous, great talk. Thank you. What are the input parameters for the machine learning algorithms to correlate LCS data? We can talk a bit more about this on Wednesday. Okay, yeah. You're apparently meeting an anonymous on Wednesday.
Let's see how long that person remains anonymous, right? Yeah, so no, I think, so usually the way, so if we talk about LCS data and we talk about PM sensors, right? I mean, so so traditionally I don't like to use machine learning for PM sensors. So I'm going to assume that this person is asking about the gas sensor data. And for the NO2 sensors, for example, we use the ramp, which measures carbon monoxide, nitrogen dioxide, sulfur dioxide, or nitric oxide, depending on the ramp, ozone, temperature, relative humidity, and CO2. And it's a bit of a black box approach where we throw all of these parameters into the random forest model, right? But actually, I should have included that slide. Naomi Zimmerman did a really nice analysis on what parameters are important for NO2, for example. And I think one of the big temperature, I think relative humidity for some reason was an important parameter, but the which you could think about as, morning rush hour peak also coincides with when it's still humid, I guess, I don't know. And then the air dries out during the day when the NO2 concentration goes down, possibly. And because there is a pretty sharp downward pattern to relative humidity as well, similar to NO2. But the other thing that is actually makes physical sense is carbon monoxide. And in an urban area like Pittsburgh, vehicles are the major source of nitric oxide, which gets converted to NO2. And carbon monoxide is also emitted by vehicles and by those vehicles. And so is carbon monoxide and NO2 are covariant. And so that might be a better predictor of NO2. With the clarity nodes, we don't have that luxury. We just have temperature and relative humidity. So we're pretty constrained in terms of what we can put into our models. But again, there are various other things. So again, we look at, I think there was this very nice paper recently that talks about, don't try to explain machine learning models, try to build, transparent models that make sense. And I think that's right. And that's what I try to do, at least so far as trying to explain the models, but now I'm also going towards the, let's not use random variables and just put a, kitchen sink approach. Let's try to use variables that make sense. Mm-hmm. And that leads itself to being more transparent, because obviously a lot of people are very concerned about such questions that was raised.
Yeah, connected to this machine learning, I was thinking you cannot train the machine learning algorithm in Pittsburgh and then take it somewhere else, because that's not going to work. And I'm thinking how much is dependent on location, in the sense, so how long and how many hours of sampling do you need to train a machine learning? And because it looks like you're bringing the low-cost sensors to the reference. But I was thinking, isn't that better to bring the reference to the low-cost sensors?
Right.
Make a tour or something like that.
Yeah, absolutely. And to be honest, that's sort of the original idea that I had for when we wrote the EPA community monitoring. So EPA had a call, we got a grant for air pollution monitoring for communities project. So when we wrote that proposal, the initial thought was, well, we'll put a network of sensors and we'll take our mobile air quality lab, go to each station, and for a few hours, and that way we'll calibrate the sensor, right? So we didn't go quite that way. What we started with was actually putting the sensors out at the Carnegie Mellon location that I showed, and we ran it for a couple of months or 3 months or something like that, because we hadn't found sites yet. So a lot of this, serendipity, opportunism, whatever you call it, right? And that data set that came out, and Naomi at the time was involved in another project, but she was facing some roadblocks. So she was like, well, what else can I do with my time? Looks at this data set, says, okay, let me try and play around with this stuff, right? And comes out a couple of months later and does some really nice analysis. And basically what we found is that you have pretty high errors with very short durations. So what we did was, the ramps actually are passive sensors, okay? So if you look at the T90 curves of these gas sensors, they're typically a minute, maybe 2 minutes, so you can't really catch sharp spikes. And again, there is some hysteresis. And so we are like, okay, fine, ambient air quality, 15-minute averages in typical locations is fine, let's use that. And she looked at the performance week by week, 1 week of collocation, 2 weeks of collocation, so on and so forth. And we found that basically you need at least 4 weeks of collocation with 15-minute averages to get best data quality out of these sensors. Beyond that, it's not, the returns diminish pretty quickly. And so we typically use, obviously with a 4-week collocation, you can't simply drive up there and leave your van parked for 4 weeks. You could, but when you have 50 nodes, that's 200 weeks of measurements. Nobody wants to do that. But the other way that also we looked at it, approached it, was if we trained it at one site and we applied it to another site, how does the performance diminish? And for Pittsburgh, we found that it is within the uncertainty of the measurements. And so even, this could be because Pittsburgh, we actually stuck it even next to okay, so this is, but one thing that we did was to develop a calibration model that's at a near source location in Pittsburgh, which is the Claritin Coke plant. And the other one is in an urban background location, which is the Carnegie Mellon campus. And so we had a source region and an urban background region. So this is sort of spanning the range of expected concentrations. And then we tested it also at a highway location. And maybe this speaks to the effectiveness of EPA's car pollution controls, that there isn't a whole lot of really small particles coming out of cars, or they are not big enough in terms of mass, or they are too small compared to the uncertainty of the sensors. But the models that were developed at the urban background location and the source location were good enough for the highway location or any other place. So we don't necessarily need to develop a model for each location in your 50-node network. We just need to so there's some intelligent design is real, right? Just going to rankle a few people by saying that. But we can be the source of the intelligent design and say, pick some source sites that are smart and actually capture the range of pollution that they expect in the city, develop your calibration models there, and then apply it to the rest of the city, and it'll work pretty well.
Okay, I think we had one more question at least I saw earlier. Oh, more. Andrew is asking, is there any hope of a general correction with an ML model so that calibration need not to be done in each location? What other variables are most critical?
Yeah, great question. So this is actually so Naomi wrote the first paper. The second paper was written by Carl Mehlings, and he developed a generalized calibration model for the ramps, because Naomi's paper did a calibration model for each ramp. Okay, and again, which variables might be most critical. I should really have shown Naomi's graph, but this depends on the pollutant that you're looking at. So for something like ozone, temperature might be more important, but for NO2, CO might be more important. So it depends on the pollutant that you're looking at, the co-emitted or covariant parameter that you're measuring. We were like, we're not going to develop a calibration model for each box. We actually did, but then we said, okay, can we be smart? And because we are developing a bank of sensors, and they are all, the beauty of mass manufacturing is that they're fairly precise compared to each other. And AlphaSense has gotten better over the years in terms of reproducibility. And so Carl did a really nice piece of work where he took the median response from collocated sensors and built a model based on that. And that's a generalized ramp calibration model. And he found that it actually works reasonably well. You might sometimes experience a little bit of accuracy, accuracy, but that's within uncertainty usually. That's the trade-off. But also the generalized model, so if you build an individual calibration model, that tends to be that can be overtrained, if you will, right? And when we build a machine learning model, what it's, in my mind, what it's really doing, and again, I'm not a computer science guy, is what it's really doing is picking up patterns in the data. And the patterns of the data come from not just the pollutants, but the pollutants come from the source mix, right? And so if the source mix and the time of the source varies from location to location, it might learn one pattern at one location, apply it wrongly to another location, right? If it's overtrained. But if you have a large bank of monitors and you try to capture a median response, so it's not driven by extremities and sensor response, which is a key thing, it actually transfers more easily to other locations in the same city. we still find, again, like the PM sensors that I showed earlier, a localized city-specific calibration is important, but intra-city transferability is actually pretty achievable.
Okay. Great talk, Subu. You touched on this some, but has there been work done to determine optimal numbers of reference monitors in a given region?
Yeah, that's a great question. So I think it depends on the purpose. Okay, so the rule of thumb is that you need one PM 2.5 monitor per million people. I mean, it's not a coincidence that Paris has 12 or 13 NO2 monitors for a city of 12 or 13 million people. But these are reference monitors, which are more expensive. And so the idea is, if you have low-cost sensors, can you actually get, good, better performance from the network than from the reference monitoring network, right? From the low-cost sensor network. How does a dense network of low-cost sensors compare to a sparse reference monitoring network? There's a couple of ways to approach this, and that we have looked at it. One is with trying to convert satellite AOD to surface PM 2.5. And we were able to do this in Pittsburgh, where we had 50 nodes, right, at one point. And it varied from 30 to 50, but at one point it was 50. And so Carl actually did this in his second paper, which was looking at satellite A, that I showed a little bit results from. But basically, the error in the conversion, or rather the accuracy of the AOD to PM 2.5 conversion decreases till you get to a network of about 10 calibration points. So for converting AOD to PM 2.5, you would need at least 10 monitors in a city the size of Pittsburgh. And beyond any more than that, it's not particularly useful to that particular problem. But the other way to look at it is there are other pollutants, and how well does a network of sensors actually capture, say, population exposure? And this was work that was done by Rose Eilenberg, who just finished a PhD from the Department of Mechanical Engineering, advised by Alan Robinson, co-advised by me. And so this is looking at the value of information from a network. And what we find is that for pollutants like ozone, a high-density, low-cost sensor network doesn't really make sense because ozone is a secondary pollutant. Across a city, it's really not going to vary a whole lot. A few ppb at most. You might actually see some ozone titration at near roadsides, for example, where it actually is lower than what the urban background ozone monitor measures. So which actually is a good thing, right? It's not a bad thing, but from an exposure perspective. But for something like NO2, which is much more heterogeneous spatially and really tied to roads, you really need a high density network. I forget the exact numbers that Rose came up with. I'm happy to share that link to that paper. It was published in the Journal of JESEE, and yeah, it came out this year. Particle size distribution, we haven't yet looked at. That is something that at some point we need to do. Ultrafine particle number concentrations, that is something that Marco Kulmala at one point told me we should do. And a lot of places in Africa don't have that. So at some point, yeah, we'll get to all of that, maybe.
My lab has used both popular and modular sensor, and are working through which is better, which we should focus our effort on using. What is your preference?
I do not endorse any manufacturer. Okay, I like both Adrian and Eben. They'll both kill me if I choose one or the other. No.
Okay, but pass on this question.
No. Well, I mean, I can actually, I think this is, I can definitely give a shout out to Evan and David and the work they're doing. which is, I mean, so the perp layer is basically a plant tower sensor, right? Or two plant tower sensors inside. And perp layer is not, as far as I know, applying any actual corrections to the data. They're just pushing out whatever plant tower reports. And I think if you go to the perp layer website, you can actually have an option of which correction factor you want to apply, which is a nice feature that they have added. The modular sensors, they use a perp layer, a plant tower sensor, and an alpha sense OPC N2. And they actually bring some, aerosol chemistry into it. And the details, you can go talk to Eben about it. I do like the modulars a lot. At least in Accra, they worked really well. One of the disadvantages to using the plant tower as used in the perp layer, a lot of lab studies have shown that they don't really reflect the ambient size distribution. So if the size distribution changes, the perp layer doesn't I shouldn't say perp layer, the plant tower doesn't really change in response to it. Okay. And so for a place like Qatar, where I am in Doha, where there is a lot of supermicron aerosol, the plant towers based low-cost sensors are SHIT. And and so you really need like we are hopeful. I mean, we're still evaluating the modular in Qatar, but when we ran the modular in Accra, they worked really well. And so, if you can afford a modular, you get the plant tower sensor plus the added bonus of the OPC and the chemistry expertise that Eben and David bring into the picture. So, if you can afford it, but, they're also more expensive than a perp layer. But yeah, I mean, there was also a recent paper from, I think, Becky, I forget her last name, Alexander, I could be wrong, but at NOAA, and, with others as well, who basically did a very nice job modeling a perp layer and finding that it really doesn't respond well due to the optical configuration for aerosols bigger than 2 microns. And so even for PM1, it's really a PM1 sensor. And so if you have any chance of supermicron aerosol, it's not going to work for you.
Okay. Very interesting talk. Tropomy NO2 data was recently updated to bias issues in the first version of the retrieval. So please check that. Further, I'm very interested in comparison with satellite data with low cost sensor. So let's plan a meeting on that.
Yes.
That's Peter Nell, I believe.
Okay, great.
At KNMI, NO2 sounds was developed every 10 meters. So yeah, cool. Peter Nell is interested and wants to talk more tropomy low cost. Awesome.
Yeah. So actually, on the vertical profile, we actually were able to stick a ramp on a balloon in Paris. And so this is the balloon Generali, which is a tourist balloon, and at the Parc André Citroën, and it goes up 150 meters, stays there for 5 minutes, and comes back down. It's a nice tour. You get a nice view of Paris. Lovely. Recommended if you are there. But they also have an ozone monitor from LISA and a LOAC. But the monitor, so we are able to put a ramp there as well. And we got some very nice vertical profiles of NO2 and ozone from that. And the ozone data from the ramp actually closely tracks the reference ozone, which I think is a 2B Tech monitor, reference monitor, but the ozone tracks the vertical profile from the reference monitor pretty well. And the NO2 shows a very nice bump in the first, tens of meters, and then it sharply reduces because of titration at the upper, because there's NOx emissions near the surface from all the cars. And then above at the higher levels, it reduces significantly. And this is the measurements that we did. And I haven't really converted that into a paper because not enough time in the world, but definitely some really interesting results that we found. Up to 10 kilometers, sure, definitely, worth looking at, but yeah.
Yeah. Okay. And we are almost 15 minutes late, but it was totally worth it. Thank you. Thank you, Subu. Thank you, everybody, for asking questions and following the seminar. See you next time in 2 weeks.
Thanks so much. Thanks all. Thanks for the questions, and thanks, Ali. Good seeing you. Bye.
Bye-bye.